today. We can do some computing examples in class. Before then, if you wanted to try to install RStudio and R and enter a little small data set, you could do that. With an internet connection that's not too slow, it doesn't take all that long to get it going, and then we'll see if you have questions about how that goes. Right? So, for today then, 28, 19. So Monday we kind of talked about statistical models and the idea of a model that we're going to propose something that represents reality, that has some random components to it, and use that to try to understand some things about the world. Today we're talking about making statistical conclusions, and kind of the broad outline of how going about doing that. And within this outline of making statistical conclusions, we'll look at a lot of different statistical models and how they get used with data and how we do the inference over time, right? So the steps in a statistical study. Basically, there's 4 primary steps. There's a hypothesis about the populations. Sometimes we have hypotheses we want to test or evaluate. Sometimes this would be phrased as some type of critical questions that we want to try to address. Does something impact something else? Are there differences between groups and so on? We're going to get some data. Maybe that comes from a randomized experiment. Maybe it comes from an observational study. So there's different ways that we can get data. Increasingly, you can get data from different sources on the internet that probably were created originally for other purposes, just tracking, reporting, some program operations. Then we're going to do a test related to these hypotheses. In general, this is some type of inference generalizing to a population. Right? And then some decision at the end, some decision or conclusion about that. Right? So that's the broad outline, and so we'll see hypotheses phrased about a number of things, and then data that's appropriate for that, and then work out a statistical inference procedure and how we summarize and check things like that. Right? And as we talked about last time, sometimes the hypotheses often will be about models for things going on. Are there group differences? Is there a linear relationship? Are there effects of one way or another of some predictor variables on some outcomes? And how does that work out? Right. So the book has a couple examples in this chapter 1. One, they have a randomized experiment of whether this was it's about motivation and creativity. And the motivation students were given, if you looked at the chapter, that they were even given an intrinsic motivation, like you should do creative writing for your own benefit because it's valuable in and of itself and so on. Or they were given an extrinsic motivation. You should do this because you'll get a good score, you'll achieve things, you'll get good grades, or something like that. Right? And so more a reward type thing. And then they had, there was some, the group, there's students, right? And then they were randomly split into those 2 groups. And then there was an evaluation creativity of poems that they produced. Right? And it turned out in this case that the intrinsic motivation, rather than to get a reward, those poems by judges who did not know which motivation they were given, so outside of that, kind of more objective, judged the poems to be more creative on average. Right? Some were more creative, some were less creative, but as a group, their average score on creativity from these poet evaluators was larger, right? And so, right. But this one, you might, the question that we're looking at is, does it fit this model, right? There's some hypotheses that one type of motivation or another could produce a difference. Right? The data become how many individuals get each of these along with their scores on the creativity, and then they do a test. And so that's some of the technical side of things. They do a t-test for difference in means. And they report a p-value that they report is very small. And we won't really go over the details of those. We'll do more of that on Friday, along with computing it in R. But those components fit into this test, right? That they have the averages, comparing the averages, and subject to the randomness in the measurements. The average difference is convincing, that it's big enough that it doesn't appear something that would just be done by chance. And so there's a process of doing this inference and this evaluation that says the chance that we would get actually this difference is quite small. Right? And if it really were the same, and therefore that's quantified in this p-value and it's small, and so the decision that's done is we can conclude that it does make a difference, and the intrinsic ones seem to give more you have a better effect in terms of that dimension of things. Right? Right. In contrast to that, there's an observational study as the other. Right? So that's one type of study that's used here. In the observational study, they have a bank with clerks, and they have female and male employees, and they look at starting salary. Right? And it's observed that the female salary is lower than the male salary on average, right? But this is one bank and it's one group of people, and that's one factor. There's no kind of random split by gender. You can't do that. It's just immutable characteristics. Well, that in this case, in this study, right? And the question, even though you see an average difference, does it convince you? Can you make a conclusion? Right? You could implement the mechanics of doing a t-test for a difference of means, and under the usual scenarios, compute a p-value, but does it mean the same thing as having this randomized experiment? So in this one, there's a difference. If you do this t-test, it's also statistically significant. It appears more than chance. Right. But is there anything, just hypothetically, that might influence a difference in starting salaries? Yeah.
Experience.
Right, so there might be some difference in experience, right?
Yeah, well, I was gonna say, it's kind of similar to education.
Education level, right? So major, did people take certain classes and things like that, right? Yeah, so that's some of it, right? And so in observational studies, there's this issue of confounding variables. Right, so confounding variables would be these ones that possibly disturb what we can make in terms of conclusions based on data in this test procedure. Right? So if, just hypothetically, the men had taken more internships or had more work experience, right? So their starting salaries after that period of time, when they're starting full-time, might be higher, right? And there wouldn't be any deliberate bias there. Maybe the education, maybe they've taken different subset of classes or different major, or had a particular faculty member or somebody do a good recommendation, and as a result of that, the salary is a little bit higher. Now, that's not to say there weren't societal biases and other biases that led to that initial difference, but the challenge within observational studies is that these things could be different by group, right? And they could affect the outcome. And so an apparent difference associated with the female-male division here could have some explanations, but that maybe in the context of that business makes sense. Maybe it does translate into performance or achievement or expectations that have a rational basis in terms of things. If people have taken certain classes and have more prior experience, maybe it's true. There could have been a societal bias that limited the amount that one group had versus the other, and so that's still true. But after that point, maybe the offer of the starting salary was rational in some way. Well, what about a variable like hair length? There might be an average difference in hair length between these two groups. And if you look at hair length, we classify it as long versus short, and then starting salaries, maybe you would still see a difference, right, in average starting salary. So hair length could kind of, in some ways, be thought of as a confounding variable, right, in some technical definition of things, right? But it is different by groups, and the outcome is different by groups, but would you ever consider adjusting for that factor? Is that a rational factor in terms of setting salaries? No, I mean, so it's not a stand-in for female-male because, of course, it's not that binary in terms of hair length. But I would say it's not a rational or justifiable variable for consideration. That it would be hard pressed to come up with any rationale why that in by itself would associate with salary. It might be some of these other things that you had two women or two men and you saw one of them had more experience and one of them had more education. Well, you can understand possibly why one would get a higher starting salary, but this variable applied to either subgroup should not make any difference, right? So observational studies often have this, that there's a lot of potential variables for things, and it comes up in a lot of important circumstances where there's a choice process and a justification process. That sometimes the differences can be explained, but sometimes there's still some residual difference after a model is used that tries to explain that, right? So the So the data can come from different things. We'll learn about a procedure for doing a test and doing an assessment of significance, but all the decisions and what we conclude really depend on the type of study that is there. It almost goes beyond the kind of mathematical formalism of things, right? And, right. So we're doing all this statistical study really to make some inference about a population. So inference to populations. That there's, we can think of a larger group to which we want to say something, right? Does the pattern that we see in the data that we have really generalize and hold true in a broader population, right? If in general, giving students intrinsic motivation for writing and creating things, does that lead to more creativity, not only in this classroom, but in other classrooms, in other fields, maybe other age ranges, and so on like that? Is it something that's true in that, right? This is one bank. If this is true across other disciplines, you know, what we see, this apparent bias here, if it still holds up after adjusting for reasonable, justifiable things, is that still true in the broader population, right? So one thing that the book says, right, is that inference to population can be drawn from random sampling studies, but not otherwise, right? That you can take things from a random sample from a population, evaluate data on them, and then generalize. I'm not sure that that's really how it goes a lot of the time in practice. Very rarely do we get a perfect random sample, right? So even in the context of, the book says, inference to a population, right, can be drawn from a random sample, from a random sampling. This is actually the quote. Sampling study, but not otherwise. So I think we can think about that in a few contexts, right? So if we have a sample survey, right, we could define a population. So things like the current population survey lists all the households in the United States, right? And implicitly could select any adult in the United States to, citizen or not, to be part of the study, right? And so they use a random selection This random selection is controlled by the researcher. So it's not, just volunteer if you want to give your information and tell the government that you have a job. It's a random selection where they control which households get picked, right, for the interview, and then they go and try to interview those people and get it, that, right? And in general, the selection is representative in that sense. In the sense that every household has a chance for getting picked. We know the probability that they get picked that varies by geography often, right? And so if we use a proper weighting to account for that selection probabilities, it should be the average, assuming everybody responds, but there's non-response. Right? Some people don't respond, right? Things like the current population survey or American Community Survey or other large government surveys often aim for about 80% response, right? So 20% of the people don't respond. So in a way, that's not completely random sampling, right? The people that don't respond have made their decision not to do it. So there's a chance, like with confounding variables, that the people who don't respond are different than the people that do respond. Right? If the 20% who don't respond are all unemployed, that would seem to be a bias, right? That Confounding variables related to that is bias, so confounding bias. And so in this case, it might be a non-response. There's a potential for some non-response bias. That the results that you would get from the respondents might systematically differ from those that don't respond. So your estimate of the unemployment rate is not accurate in that sense, because one group, maybe the unemployed or the employed, one group or the other, maybe the employed are too busy to be bothered with this, and so they're running off to their jobs, so they don't answer. It could go either way. Right? But despite that, this is the source of the nation's unemployment estimates, right? Every month for the nation and for many larger metro areas in some states. Right? And there's this non-response problem. So it's still viewed as relevant. There could be a little bit of different, right? But we still take it as we believe it tells us something useful about the population. Right? I've been involved in surveys of the Veterans Administration healthcare enrollees. Right? So these are surveys of veterans. There's 8.7 million veterans in the US. For this survey, they interviewed over 42,000 of them, but it's only a 30% response rate. They contacted them multiple times in multiple ways to try to get people to respond, but a lot of other surveys have really dropped down to a much lower rate. But still, the things that come out of this survey, although there's potential great bias, right, it's still going to be used to make decisions about the population. Right? So things that are getting bad ratings by the healthcare enrollees are still going to matter. Right? And whether it's exactly like the population, so over time, they're going to repeat the survey every year. So even if there's this bias, there could be an assumption that the bias is similar each time. Right? And if anything that's really trending up or really trending down, they're going to do a test. Right? Have things gotten worse on any particular measure, or has participation rate in mental health services or something else really changed in this sample? So they will do this test and come up with the decision, even though it's not really a random selection from the population. Right? In some ways, we still believe that what we're getting out of the study is useful. Right? It has to take with caveats that it might not. There's some part of the population that could potentially be different, but by and large, and some people just don't respond just because they don't feel like it or don't like doing that. It wouldn't necessarily mean that they would have any different use of healthcare or attitudes about healthcare. They just don't deserve it. Right? So sometimes sample surveys, even though that is set up to be very much in this setting, has complications. We still go ahead and use it. Another limitation is, in randomized experiments, a question comes is where do you get the subjects? For a study like this, so the randomized experiments, say the one in the book, where did those students come from? Were they really randomly picked from some population or not? Well, probably not. Right? They were involved in college classes, doing writing, and maybe they randomly split by classroom, and some classrooms got one form of a survey and other got another form of survey. Or if it's online, I could give you different surveys in the same classroom, right? And you might talk to each other and figure out that you had different surveys and talk about that experience. And that kind of muddles the treatment, that it's not as purely one thing or another. But generally there's volunteers. And still, if you see a big difference between these two, and we evaluate the randomness of it, and it still seems like it's more than just chance, and the p-value is small, so we make a decision, right? We still believe it, right? To some degree, right? In graduate school, there's a professor in psychology, Bob Rosenthal, and he always says you generalize from like to like. So you have what is your sample like and what part of the population does it represent. And so you can make a conservative statement that, well, it's maybe other classes at this particular college, if it was done at one college, would have a similar effect. Right? Or maybe similar classes across similar colleges. You know, if it was done at a liberal arts college, would it apply to a research university type setting? Maybe it would. Right? Would it go beyond just students in four-year degree programs? Maybe it would apply to college, community college, associate's degree programs, or maybe high school, continuing adult education. So there's at some point where the conclusion makes sense, and then it becomes limits. Right? If you run into teaching, writing to English as a second language, and this was tested on a group doing creative writing and poetry classes. There might be a difference between those two. It might still hold up. Maybe you should do a random experiment on this other population and see if the effect is consistent. Right? And so sometimes you still believe that the randomized experiment results, even if you don't. Right? I worked with some colleagues when I was at George Washington University, right? And they were doing randomized, well, they weren't even doing randomized experiments. Right, so, so a different randomized experiment at GW as well was called the Diabetes Prevention Program. So this study took people from 27 different centers, medical centers across the US, Hawaii, Los Angeles, Florida, Massachusetts, Chicago, Louisiana, different places all over the place. And so we had a bunch of subjects. They were evaluated and were pre-diabetic. Right? So they had blood glucose measurements from fasting glucose that were above 100 but below 126. Right? So if they go above 126 and that's confirmed, they're classified as diabetic. Right? If it's below, it's normal glucose. So they had been evaluated thousands of people. They got about 3,000 some and more. And these people were randomly assigned to a group. One got a placebo, one got metformin as a pill, and one got a lifestyle coaching. Right? About 1,000 in each group. And they followed them for 3 years. Right? The patients had to consent to the testing and consent to be part of the study. Right? The placebo ones got a pill that looked very much like the metformin one, and so on. These subjects really came from about 27 different centers, and they were volunteers. And for ethical reasons, they had to consent. They had to be told the risks, the potential benefits, and that this could make a choice. And if they had placebo or metformin, they couldn't really tell which one they had because they got a similar looking pill. But anyway, they're going to be evaluated several times, right? And the conclusion was that there's a huge benefit from being on the glucose-lowering drugs of metformin or changing lifestyle to decrease fat and sugar and just eat healthier in general and to be more active, right? On this group. But it was not really a random sample from the population. But it was a pretty diverse group, right? They had a couple of these were at Native American Indian Health Service sites. So they had some Native Americans, some were areas that had many Hispanics, others had many African Americans. There were some in New England, all over the place. Right? And so in some sense, this was a little microcosm. It wasn't really a random sample, because it's not really a random sample from the population. But in some sense, it represents a big group. Right? And to the degree that there were big effects of doing either one of those things after just a few years, the idea is that we would believe, right, gather the data, look at the observed differences, try to judge if those observed differences are really big, bigger than just chance alone, that it wasn't just a fluke or just something just by random sampling or assignment that seemed to make it happen. But it was, it's still believed, right? There are limitations, right, of randomized experiments like this, besides not really being, a random selection from the population, even though it's a pretty diverse group, right? These are volunteers. They are informed that they're in a study. It's not like they're just going to their primary care physician and their primary care physician is saying, this is what you should do to be healthy. There's not that kind of they know there's an experiment. They're trying out something that hasn't been proven quite as well. It's not kind of the standard of practice yet, right? There's some dropout, right? Some people were kind of too sick for other health reasons and were quickly out of the study. Right? Some people couldn't stand the drug. Right? They caused gastrointestinal problems for a small selection of people, right? So they were out. So there's a few things. Some studies have worse dropout than others. There's some placebo effect, like just because you're doing something, some people seem to get better, right? Just if you're giving them a pill and they're saying we're gonna, they've learned that this is about lowering blood glucose and being healthy. Well, they can read the news, right? They can see things. Maybe they pay attention to it a little bit more because they're in this study and they're a little more active. So there's limits to an experiment like this, but in the end we're going to go through that same process and observe a difference and try to evaluate it statistically. Is it more than chance? And then come up with a conclusion. And so we'll have our statistical conclusions, but in any real thing, it's in the context of the overall, scenarios for things, right? Other things, we don't necessarily even have a randomized experiment, and we don't necessarily have a random selection. But I would say that sometimes we still can look at data and come to the conclusion that there is an effect, right? It's harder, because if you're lacking the randomization to treatment or the random selection for a population, you have less control. And the confounding variables and biases you had to begin with could play a bigger role. And even if it's not clear what they do, in people's minds or people who want to criticize the study, they could say more about that. So just two brief examples of where we might conclude things, right? When we don't have any of this randomization. So in health studies, right, there's conclusions many times, like smoking causes cancer. So U.S. Surgeon General, right, said that in 1963, right, that smoking causes cancer. Right? Why did they say that? Was there any randomized experiment that had some people smoke and some people not smoke? No. I mean, was there any really random survey asking people about their behaviors or things like that? There were different data collections, but it was all observational studies, right? There's many potential confounding variables. Right? What would be an example of a confounding variable that you might think of in terms of evaluating whether smoking causes cancer? Yeah.
Like family history.
Yeah. Right, so family history. Maybe some families are just simply smoking families and everybody gets together and everybody smokes and they just have a family history of cancer. Maybe there's no causation, right? So that would be a possibility. Anything else?
Maybe like common complements, like items that people consume, like they also smoke.
Yeah, so diet, alcohol, So maybe it's not that they're smoking, maybe that they're also drinking. So the people that are smoking tend to do it when they're out drinking, and maybe it's really the alcohol. One of the first early calls I got about a potential consulting project was this is back in the 90s, 1990s. It was saying we want you to help provide statistical arguments that asbestos doesn't cause, or is that asbestos is not at fault for cancer. Well, so anyway, it was a cancer, and the asbestos industry fighting the tobacco industry over who was most responsible for some lung cancers. I didn't get involved, but there are statisticians who do that, but it sounded kind of fishy. But anyway, diet and alcohol could be other things. Yes.
Could how much you smoke a day be one?
Yeah. So
Or
a
how much
key
you
thing
smoke.
is that amount of smoking. Right. So that's going to be a key variable, right? So did they smoke? One per day, only occasionally, how many years? Yeah. So some quantifying that of how much do you have to smoke versus it happening. It comes part of the question, right? That rather than calling that really a confounding variable, it's a big complication in how you define the groups. Are they ever smokers versus never smokers? Or have they smoked more than 10 years? Or there's the measurements in the smoking industry. Have you smoked 100 packs equivalent over your lifetime? At a certain point, you cross a threshold for consideration of some of these groups, right? There's a status of heavy smoking. Do you smoke more than 15 cigarettes a day? So it seems like a lot, but some people that smoke, that are chain smoking, are getting way past that. So amount of smoking makes it very complicated to say, maybe some people smoked for a few years and then stopped. Well, are they counted as smokers or non-smokers, right? So it can be very complicated there. Of doing that comparison. And if you exclude the people, well, yeah, so you could either make the differences between the groups probably look big. You take the people that have been smoking 30 years versus the people who have never smoked, well, that's a pretty big difference, right? But if you take the younger people who have smoked some versus the ones that are currently smoking at age 30, something like that, right? Well, there's going to be less differences there. The effect might be different. And then the assessment of significance, the testing that we're going to do, is going to be affected by those choices, right? But environment certainly can do this. If somebody lives in the center city, and at that time gasoline had lead in it, right, and a lot of it was much more toxic than it is now when they did the early studies. Work environment. If somebody works in something with a lot of, let's say they're working in a paint factory, right, with a lot of toxic fumes and things involved in some of those, so maybe say, oh no, it's not that. So, but even though these were observational studies, once they looked at a huge number of other variables and divided it by age, right, and by female, male, and other categories. Back in 1963, I don't know how much the initial studies looked at race ethnicity differences. They might have all been done on white men, and that was a bias they would have had. But still, they would have come up with I think it also, certainly the later studies were done on women too. But if you adjust for all those different things, there still appears to be this difference. And so it becomes more work and more effort to be convincing and get a good conclusion with confounding variables and observational studies, but sometimes you can still do it, right? So a more modern question. So anyway, the conclusion of this is, even if, no matter how you divided it, and how you took more subtle definitions of the groups, and you still had the ones that smoked more, got more cancer, more lung cancer, and lip cancer, and throat cancer, and things like that, right? So it still was there, so the conclusion was, yeah, that has to be it. There probably were some biological studies as well, are there carcinogenic chemicals being consumed in burnt tobacco, right? So you can do that in a laboratory and say, yes, it does produce things that are carcinogenic when you put in a petri dish, and so it very well might transfer over to humans in real life because we see it there in the biology lab. That would support any of the statistical studies. Are minorities, right, stopped unfairly, by police? That's a question we want to answer, right? There's every once in a while articles come in the news. So in the spring of 2018, Connecticut reported through an open data initiative all the traffic stops it had made during the year, and minorities were overrepresented, right? And can we evaluate that? Right? You can certainly do the numbers and say the percent of minorities in the state versus the percent of traffic stops. Does it match up, or is it higher? You know, percent minorities are higher among traffic stops than they are in the general population. That certainly is true. But in terms of our statistical study, can we say that it's more than chance? And can we make a decision? Right? So is it more than chance? You could use some of our statistical methods to try and get at what is the distribution of likely rates and comparisons. Is it, if minorities are, 25% and 27% of the stops are minorities, is that too much? Maybe not. If it's 35%, maybe given the populations, that's more than chance, right? So, kind of dealing with relative magnitudes and what is plausible. But some of the debate in the newspaper really is about confounding variables. Right? Is there anything that would explain why one group gets targeted, or not necessarily targeted, but just stopped more than the others? Yeah.
Geographic location, maybe?
Maybe geographic location? So, meaning what?
Meaning, like there's certain data models out there right now that, try to predict where crime are going to be, and they'll send more of their cops there. So,
Yeah.
and if that happens to be an area with more minorities, then it could look, it could end up confounding the study. But
Right, so if there's, if something says this area is impoverished, and poverty has a lot of crime, or there's not a lot of unemployment in this area, maybe there's more crime, so police, right, so there might be some factors like that, right? A challenge comes with this in terms of what do you adjust for, right? So if you target areas where police have made arrests before, right, or stops before, right, and put that into a data model, right, so that might predict more crime in those same areas, and then you go back and do more stops, more arrests, more checks, and that leads to more arrests in that area, so it kind of builds on itself, right? It's not exactly the same, but the salary example adjusting for hair length, right? If you put certain things in there, it will seem to explain the benefit, but is it really legitimate? And so in the data science debate about what variables do you put in there to explain this, right, is a big deal, right? So if you put in something like, well, the cars were older or had more broken lights or something like that, that's a reason to stop cars, right? You could investigate, do cars owned by minorities really have more broken lights and problems than other ones? Or are more of their tags for their licenses, registration, are they more out of date than other groups? So you could do a study to support that as a variable, right? So if there is a difference between having working cars and registered cars between these groups, and that's why the police say they're stopping them, well, that could partially explain the difference, right? In the articles, sometimes they said, well, there's more out-of-town drivers coming from other areas. There's not as many minorities living in some of these communities, so when they come when people come from outside, they don't follow our traffic rules so well. And so therefore they get stopped more. Or maybe police are targeting out-of-state licenses more. Right? It becomes kind of subtle, you know. It's hard to know what is right for adjusting. But we'll do our statistical test, and then it's a hard question to think about how these different things should be used in a statistical model. Right? When we get to regression models, we're going to be adjust for different effects. Some of those things could be confounding variables that we put in there to adjust for the apparent differences. And so even if it's not a randomized study, even if it's not from a sample population, often we're in the situation of wanting to really make some changes, right? So, let's see, what time is it? I don't know. How are we doing? We started, we have a little bit of time, right? So, good. But any questions or comments? So, a couple definitions from the book. So by inference, we mean does the data pattern that you see in a sample does it exist? It exists in some broader context. Or in some broader population. So the type of inferential statements, we'll see something in our data, in our small sample, and want to be able to say something, right? So we look at the patterns in the data, averages, shapes, correlations, whatever we see in our sample in terms of summarizing data. What does it look like in the broader population? Right? Statistical inference, then, my little abbreviation for statistical, is we have a probability model in statistical inference. The probability model is used to link the data pattern to a larger context. Right. And so the probability model gets used in there, like our data or independent samples of a certain size. Maybe the data are normally distributed. They have a certain average, standard deviation. So within the context of that probability model, we're going to make a way to link the data pattern in the sample, to link the sample data pattern to the larger context, to make the inference kind of through what that model implies, right? So in this, we essentially evaluate the range of possible scenarios, possible situations. In the population, that is, what does the population look like? Through implications, implications of the model. The model and its description of randomness. So our probability models will allow for some natural randomness in the population. Right? Not everybody's weight's the same, not everybody's experience is the same, so there's variability. And these models will have a probabilistic structure on the measurements, or at least some part of the measurement structure. Sometimes we relax that to try and make it less tied to that or less restricted by the choice of a particular model. But that model describes randomness, and we see some data, And so, given a certain assumptions about the model with our data, only certain conclusions about the population seem reasonable. Right? That you're not going to see things that are massively different from your data in the actual population. Right? So this process to kind of revisit the steps at the beginning of analysis. To do this, we're essentially going to have some steps in our statistical inference. Right. We're going to set up some null and alternative hypotheses. These hypotheses often are about a parameter. So the parameters then are characteristics of the population. They're often going to be our symbols, like mu for the mean, or pi or p for a proportion, or rho for a correlation, some description of the population. We're going to have those hypotheses. The null hypotheses, the null is usually no effect, no status quo, no difference. That the population we're studying or the situation is unchanged from what we already know and from what is the past history, or there's no difference between groups and our intervention or our effect is not really there. Right? And the alternative is that there is then some effect. Sometimes we're checking to see, we hope that there's no effect, but often in medical studies or in agricultural studies, you're doing some intervention or education, right? You're doing an intervention and hoping to make things better, right? Or you're worried about something and testing, has this had a detrimental effect? And is it worse? So the alternative is some difference that's there, right? We get some data, and from that we calculate a test statistic, right? Which is some summary of our data. So if the parameter example is the population mean given by this Greek symbol mu, our test statistic could be just the sample average, x bar, right? Has an estimate of that, right? And then under different assumptions about the model and what the population looks like, some of what is informed by the null hypothesis there. Right, we're going to look at the distribution of this test statistic. Right. Under the null hypothesis, under or assuming the null hypothesis is true. Sometimes this is called the null distribution. Right. It's a distribution of that test statistic that is in this chapter 1, they deal with a permutation test, which is a randomization mechanism for looking at what is that distribution of values. And so it's called sometimes a randomization distribution. And so by distribution, right, is meant in here the probability distribution. What values are possible and how likely are the different values? Okay. Distribution, into this word, is really a probability distribution. So the possible values, right, and how likely are they? And so once we set up this hypothesis, get our data, and figure out how to assess this distribution, either through simulation or maybe through theory, then we're going to calculate a summary. P-value is one summary. Other confidence intervals and other things are summaries. the book right now is calculated on p-values, right? So it's going to be a probability of seeing something as extreme as we got or more extreme under the null hypothesis or under the null distribution. Okay. So it's kind of a mouthful. You've seen it in other contexts through statistics if you've done any sort of testing. Right? But the p-value is going to be computed. Right. So it's the probability of a result. And the results are test statistic values. As extreme or more. Then we actually then our sample test statistic value. Right. Assuming the null hypothesis is true. So that's why we figure out the null distribution or the distribution of the test statistic under the null. We're going to look at is it very unusual or not. Right? And then we make a decision. All right. Next time I'm going to bring a couple more markers so I get some more colors. I'll try to figure out why I couldn't get that to work. Right? The decision is usually if the p-value is small, if we've gotten a really unusual result under the null hypothesis, we reject the null hypothesis. If the p-value is small, right, reject the null hypothesis, which is H0. Null is H0, alternative is H hypothesis 0 or hypothesis. So it's something that's really unusual and has a very small probability of ever happening under the null hypothesis. As we've interpreted it, given what our data said, what we've observed, and what the model means and how it translates into this distribution of the test statistic under the null. If what we've got is outside of reality under the assumption of the null hypothesis, and that means a small p-value, we reject it. I conclude there has to be a difference, and whatever that implication is for policy or behavior, we have to think about that. All that gets interpreted with what type of study was this, and is it a limited study group or a more broad study group? Were there other potential biases? But anyway, that's the statistical contact that can be done out of that, right? So just to go over, describe one slightly more context thing. And so on Friday, we'll install R and start using that and look at that with some actual numbers and some actual data and do some of the graphs that are in the book. We're not going to explain as much of those, but we'll be able to reproduce a lot of those things and see what they mean, right? So let's say you had, as an example, 100 people with diabetes. Right. So they have a clinical definition, they're fasting, glucose, major on its scale, glucose, right, is over 126, so they're in that done, right? And then 50 people will have metformin, right? So there's consent, they agree to be part of this study. Then there's randomization, so that all the risks and realistic outcomes are explained to them and the whole procedure, what they're going to get. 50 people get a placebo. So you get, this is a well-established drug now, but when it was first developed, you would have done some small-scale studies to see is it a plausible benefit and done something like this. Maybe you've done it with 500 people in each one, or whatever. Right? And then you follow for, say, 1 year. Some studies would be 3 years. Some studies really need to be longer to assess other things. And then you look at weight loss after 1 year. So that means that at baseline, at the start of the study, we measure weight. And then at 1 year later, we measure weight again so we can get a change for everybody, right? And so in terms of this scenario here, right, we have two groups. Use of one could be average weight loss for metformin group. And use of two could be the average weight loss for the placebo group. Those are the views, they're what would be the average if it was applied to an entire population. And so our hypotheses usually are about those things, right? Are they equal? No effect. The placebo, somebody's taking a pill, they know that they're involved in some health study. Maybe they do something to improve their situation. Anyway, they read the news, they just feel a little motivated to have a little less ice cream or alcohol or walk a little bit further or something like that, be a little more active. So there might be a placebo effect, but that's part of this other group. This might also be phrased as the differences are zero. And an alternative could be that they're just not equal. We'll talk about scenarios where we might do one-sided or two-sided. Often in medicine, it's one-sided, right? In the sense that we are only interested in just getting better, right? We get data. Maybe we have 50 observations in the first group and 50 observations in the second group, and we're going to calculate an average for the first group and an average for the second group. And so our test statistic could be y bar 1 minus y bar 2. Maybe we just call that d bar for the average difference. Use some symbol for that. And it's likely that d bar is not 0. It's going to be something. And so the randomization permutation test that's done there, or the t-test procedures that we'll also do, really are interested in if 0 were the real difference. Maybe you would call this use of d, the true difference. If that really were true, based on our data, if these are our likely values of d bar, assuming that's true, usually plus or minus some, but if the truth is at 0 and you have some randomness about that, where is our actual, from our data? Is our d bar in here? If it's in there, that's not significantly different from 0. It's within the realm of possibilities. And so the whole permutation, randomization distribution, or our assumptions about t-distribution methodology will be really assessing that. On the other hand, if it's out here, that would be a relatively big difference given to the likely range of the null distribution. So out here, we really reject null hypothesis. So on Friday, we'll look at this in R, do a little bit of computing with actual numbers. If you want to try to install the programs before, that's great. You can do it also here. We'll run through it on there, so if there's any questions about things. And look at some more within chapters 1 and start to bridge into chapter 2. All right. And then, yep. So the 252 has some overlap.
Today?
Yeah.
Okay.
So as if you look at but the thing will diverge
Yeah.
pretty soon, but.
Yeah.